Welcome to that moment that you may or may not have been waiting for. I know I have. This is when we can put together all the different pieces we've been building up to and start doing hypothesis testing, sometimes also referred to as significance testing. And this is, if you've made it this far, you've made it to at least the minor leagues. I don't think you're at the big leagues yet. That'll be a more advanced statistics class, but you know enough to be dangerous. You know enough to be doing some actual research that you could potentially publish and present and all that stuff. So this is where I think the fun really starts, because this is the logic that is used to make conclusions for good and bad. This is not the perfect system. I want to also acknowledge some of the limitations to understanding our natural environment and the human existence in this way. I guess not even just human stuff, just science in general. We'll cover the good, the bad, and the ugly, and there's a lot to get through, but hopefully it'll be worth it. So here's the quick overview of what we are going to cover today. You can see there are a lot of different subheadings here, so let's keep it rolling. First of all, we'll do a review of Chapter 7, which had to do with probability and specifically probability and sampling distributions. Sampling distribution is a distribution of sample means. And how do we make a few changes from what we learned with individual scores to be able to discover probabilities and make conclusions about means. So to begin our review, what is a sampling distribution or of sampling means? Instead of a distribution of individual scores, it is taking our mean that we want to test it against something, and we construct this theoretical distribution. I call it a sampling distribution. Sometimes the distribution of means, same thing. And so we put all the potential means of that sample size that we have, so all the sample means possible, that we can place our sample mean on that distribution and see where it falls and see what conclusions that might allow us to make. What does the central limit theorem tell us? Well, basically says that we have for our sampling distribution to think about central tendency, which turns out just to be the population mean that we have. That's going to be our mean for our central tendency mean for our sampling distribution as well. So we just take our population mean of individual scores and make that our mean of our sampling distribution. But also, we're taking individual scores and now we're taking samples, and so moving from that we have to have a measure of variability. Central limit theorem also gives us our formula to calculate our measure of variability for our sampling distribution, which is the standard error, or SEM, standard error of measurement, or means. And specifically, what is the standard error? It is influenced by sample size. That's the denominator. Take something and divide it by something big, a big sample size, and you get a smaller result. So bigger sample size, bigger standard error, or excuse me, bigger sample size, smaller standard error. Smaller sample size, larger standard error. But sample size isn't the only thing that influences standard error. We have to think of the numerator. If we have a big population standard deviation of individual scores, well, that's going to also play into having a larger standard error if we hold sample size constant. And then a smaller population standard deviation of individual scores on the numerator, the smaller that is, then the smaller our standard error for our distribution of means is. So all those pieces go together, and the standard error, we can't forget, smaller standard error, bigger sample size. That's one reason we like big sample sizes, because it's an easy way to get smaller standard error. But also just the natural standard deviation plays a part too. Whether that's big or small influences whether the standard error is big or small. So let's look at the logic of hypothesis testing. We're basically setting up a game. A lot of times I'll come back to the analogy of a courtroom. Basically, with a court proceeding, we have a whole list of procedures and ways that evidence is either allowed to be brought into the courtroom or not allowed. A lot of the stuff we've been doing statistically is dressing up the numbers in a way that now we can bring it into the courtroom to make a decision on. And then, of course, we're going to say either guilty or innocent, up and down. Is there a significant difference or a significant effect, or is there not? And just like with a court decision, yes, that is part of the process, but the verdict by itself, guilty or not, is not the only important piece of information we want to consider. So we're going to do significance testing, but we also want to talk about what we'll refer to later as effect size as well. So first, the logic of hypothesis testing. What is it? Basically, we're doing inferential statistics. We have a sample mean, and we're inferring things about the population from that sample. So for a more specific example, let's say we have a hypothesis that changes the levels of organizational performance. And in this case, we've set our hypothesis around the population of just GM workers. So we're not saying all auto workers in the US, but let's say GM workers in the US. So for example, we have a known population of performance before treatment. Let's say that average performance is 25 on whatever metric that is in performance metrics. And let's see what our population would be if we gave them all this treatment, right? Would the new mean be different? And how different would it have to be? What if the new mean is 26 or 27? Is that just a real difference, or is that just sampling error? It could be either, right? So that's why we have to have this hypothesis testing scenario and process set up so we can make stronger conclusions that aren't just based on a mean difference, but a mean difference and bringing in other forms of evidence, so to speak, to help inform our decision. Now we're going to learn more about hypothesis testing and the specific steps. So basically from now until the end of the semester, we're going to be going through this basic sequence. Some of the ones we've already started to go through. So it's definitely good to get familiar with this process starting today. First of all, if we're doing hypothesis testing, we have to have a hypothesis. Now, first of all, we're actually doing two hypotheses. We have what's called the null, saying that there's no effect, and the alternative is, well, there's some effect. There's some difference, there's something meaningful happening. So for example, our GM worker performance example, we can say that for our null hypothesis, basically we give a sample the training, and that training mean is 25 or as close to 25, and that means our training didn't work. No effect, null hypothesis supported. Of course, what we want to do is reject that null and be able to say that our training performance mean was significantly higher than this non-training population mean. We reject the null, and having tossed that out, we go forward with the alternative hypothesis that there is a meaningful effect, a meaningful difference. So what is the object of hypothesis testing? We're going to use this phrase, reject the null, meaning we reject the idea that there's nothing happening. Now, we say this very matter-of-factly and definitively, but we're dealing with probability. So yeah, we reject the null, but we also, as we'll get into, acknowledge that we could be making a mistake in doing so. Why don't we prove the alternative hypothesis directly? Well, basically, this is for the same reason why we can't 100% prove that climate change is having huge effects on our economy and safety of communities around the world. It's almost impossible, if we're dealing with probability, to prove anything 100% certain. All we can do is have so much evidence to the contrary that it becomes so difficult to not reject the null of nothing happening important. And I think that's kind of where we are with climate change and other important issues too. We can't prove for sure that smoking causes cancer, but man, we've got enough evidence that we can reject the null that it doesn't. I'm going to make my life decisions around the idea that I've seen enough to not know for sure that if I smoke I'm going to get cancer, but to know that I'm pretty sure I'm increasing my probability of getting cancer substantially. So the next thing we need to do is set up our decision criteria. And this kind of means think about, again, in the court of law, not all guilty or innocent verdict, guilty, not guilty. And it's sort of like, why don't we just accept the alternative? Just like a courtroom, we don't say innocent, we say not guilty, meaning we can't say for sure you didn't do it, we've just seen enough evidence that we can't conclude you did for sure. So the same logic here. And the idea is, just like a courtroom, there's different standards of evidence that are needed, or standards of decision-making criteria. Is it preponderance of evidence, or beyond reasonable doubt, or more guilty than not? We can have different standards here. So we're setting up the criteria for, we need to see this much, and we're going to state it ahead of time, the boundary that we need to see to be comfortable in rejecting the null hypothesis once we've looked at our data. So we say the criteria we're going to use to judge significance first, and then we run the test. You don't run the test first and then set your criteria. So in this case, we're dealing with a null distribution. This is our sampling distribution. And the idea, why do we call it a null distribution? It's saying that if there is no treatment effect and the null hypothesis is true, well, our sampling mean will just fit right in the middle on our sampling distribution. If our sampling distribution is the means that training doesn't have an effect, if our mean doesn't have an effect, it'll just most likely fit right in the middle. Now, a sampling error, it could bounce around a little bit. You might get some weird stuff here and there, but most likely, if there's no treatment, we can just stick it on our population mean of untreated people and then basically not have enough to reject the null hypothesis. But what we are going to do is then set up the bottom and top, sometimes both, sometimes one or the other, the outlier parts of the distribution, to say that if our treatment has no effect and it falls into one of these extreme sides, well, that's very unlikely. It's possible. But if it falls into one of these extreme areas, what we're going to call a critical region, then we say, well, we think probably there is a treatment effect and it doesn't fit on this non-treatment distribution. And so then we're going to be able to have enough evidence to reject that null hypothesis in that event. So to put the words to images, basically we're saying that with these, what we're going to call critical regions, they look like outlier areas of the distribution because it's very unlikely, if the null hypothesis is true, that our sample of getting some sort of treatment, and we take our sample mean that had the treatment and compare it to the population that didn't have the treatment, it would be very likely to end up on an extreme end if the treatment didn't really have an effect. So that's the logic of hypothesis testing. We set up our decision criteria. How extreme does our sample mean need to be for us to be able to reject our null hypothesis? And those are decision criteria that we have to make, and we have to use some logic. There's no one right or wrong value or extreme value to choose, but we'll go over some commonly used ones. So now we have our null distribution set up. Now we need to put our sample mean on there and see if it falls in one of these extreme areas. And here we're thinking in terms of probability. Let's say our sample mean that got the treatment, we stick it on our null distribution population that didn't get the treatment, and our mean fits in one of these extreme critical areas, what's the likelihood that it would get there if there is no real effect, if it just happened due to sampling error? And the further out, the further extreme it is, the lower the probability that it just got there due to sampling error. The more likely that there's something real going on, the more extreme and away from the center of the distribution our sample mean is. So once again, are we going to set our cutoff value maybe at a somewhat cautious area? Are we going to be really needing to see a big difference for us to be able to reject the null? And again, there's good reasons to make it maybe a little bit more lenient, more likely to reject the null, or to demand an extreme value so that you can be certain, or more certain, not fully certain, that if it's out here, that you can reject the null. So let's think about this likely or unlikely question, and we refer to this as an alpha level. So our alpha level is essentially the probability and the proportion that goes along with it of that extreme ends of the distributions. And when we talk about alpha, basically it is, if we reject the null hypothesis, what is the probability that we did so incorrectly, that we made a mistake by rejecting the null? Or if you think about it in terms of the courtroom, alpha is, what is the probability that we say someone's guilty when in reality they weren't? So the most commonly used criteria are 5%, 1%, and 0.1%. And as I kind of hinted earlier, we call this area the critical region, those extreme areas on the outer edges of the distribution. And do we have, for example, 5% of the distribution in our critical region? Or do we get down to only 1% or 0.1%? If you have an alpha level of 0.1 and you get a sample mean that's extreme enough to fall in 0.1% of the distribution, think about what that means. We can be very confident, not certain, but very confident that we reject the null and did so correctly. Whereas with 5% of the distribution our sampling mean can fall into on those extreme ends, it's more likely that we reject the null, but also there's a 5% chance that we did so and it turns out that it was just due to sampling error. There is no effect. Still, one chance out of 20, we're still pretty confident if we reject the null, if it falls in that critical region, that we did so with good reason. So now we can tie this, putting probabilities into extreme parts of the distribution, to our z-values. So for example, if we have, for example, a critical region of 5% or 0.05, a p of 0.05, we take that 5% of the whole distribution and 2.5% in the low end, 2.5% in the high end. These combined are our critical region, combined alpha of 0.05. And now we can see the z-scores that correspond to this. This is some values we'll see more than once moving forward. The two-tailed test, as we'll find out, there's 5%, a critical region of 5% total, 2.5 in the upper and lower ends, corresponds to this plus and minus z of 1.96. So not quite a z of 2 for two standard deviations above and below the mean, but pretty close to it. So now that we've got our critical region set up, now we need to actually compute the statistic. So we analyze our data after we state our hypotheses, and notice this is a z-score. And I probably should call this more specifically a z-test because we're actually doing a statistical hypothesis test, a significance test. And this is why I didn't, in the last discussion, go over too much of the mechanics of the z-test formula, but here's what it looks like. Sample mean minus population mean over the standard error. And that is our z-test. And if we get a z-score, going back to the last slide, either above z of 1.96 or below negative 1.96, then it would fall in our critical region. We can reject the null and think that we have found a significant result, a real effect, if our z-score falls in the critical region. So let's work through our example. Pre-training performance population mean was 25, and we have a sample mean that's 33. So we know our 33, those people that we trained, their mean is higher than the population mean, but given sampling error, we have to build that in too. Is that difference meaningful? Is it significantly different? And now we have the standard error of 3. So what do we do now? We have two potential decisions. We either reject the null or we fail to reject the null. So let's calculate our z statistic. For our example, if we go back and calculate the z, so 33 sample mean minus 25 population mean over a standard error of, I believe it was 3, that gives us 8 over 3, and the z is 2.66. So we can check the table for what probability corresponds to that. But we could just look at, for example, that last distribution we saw, and we see that this z-test exceeds our cutoff values of plus minus 1.96, and we can reject the null in this case. So let's continue thinking about what does this z-score, this z-test, or z-statistic represent. And again, we call it a z-score. I think a z-score more as individual scores, so I like to think of this as a z-test or a z-statistic. So perhaps I should maybe change this or revise this on the slides, but as long as we're talking about using the right formula, that's what I'm most concerned with. So essentially, the z works as a ratio, and this happens with all of our statistics moving forward. What is that real difference? We know our training mean was higher than our just non-trained performance mean, but relative to the denominator, sometimes the denominator is just referred to as our error term, because now we're dealing with a standard error. And just like error, it's easier to make decisions when there are conditions of less error. So for example, think about error in terms of viewing your TV. The better the signal, the less error in getting that image onto your screen, the better it looks, right? The better you can clearly pause it and look for details. If there's a lot more error, on the other hand, on your TV screen on the signal, or more noise, then it's harder to see. It's harder to get the level of detail that you might want. Same thing for our statistics. We want a big numerator and then a small denominator. That gives us the clearest ability to make conclusions about a real effect. So let's look at the process that we've set up and look at some of the pros and cons involved. So we're talking about decisions. Sometimes we make the right decision, sometimes we make the wrong decision. Again, going back to the courtroom example, sometimes a person is found guilty and they really were guilty. Sometimes they're found guilty and they really weren't guilty. Sometimes they're found not guilty, but they were guilty. Sometimes they're found not guilty and they were not guilty. So we're seeing 4 basic combinations here. So first, let's look at the type 1 error. So type 1, this directly corresponds to our alpha. Basically, when you reject a null hypothesis, but it turns out it was actually true. Again, we're just making the judgment on the data we have. Maybe we get more data later. Maybe other people do more research on our topic, and we thought we had found something, and they find that no, maybe you just got a result due to sampling error, due to a small sample size. It happens. So the probability of making a type 1 error is referred to as alpha. So again, type 1, you reject the null, that's your decision, but it turns out in reality you should not have. You were wrong to do so. Same thing for the courtroom. You say guilty, and type 1 error means that the person was not actually guilty. Think about the other error that you can make. You say not guilty, but it turns out the person was guilty. So this is what we call a type 2 error. This is when you do the hypothesis test, your z-score or other value doesn't fall in the critical region, you fail to reject the null, but it turns out it was really true. And you never really know the chance that you made a type 2 error. All you can do is, if you're worried about making a type 2 error, you can use that to affect the decision criteria you make. Okay? And the issue is type 2 and type 1 errors, our alpha and our beta errors, are related. So what that means, if we're guarding against making a type 1 error, that means it's more likely we make a type 2 error. And if we're guarding against making a type 2 error, that means we open the door and make it more likely that we make a type 1 error. So there's lots of examples we could apply this to. Let's look at the next slide for the actual decision table. Okay, so let's see where these pieces fall. We have reality, and we have our decision based on the information or the numbers that we have. So let's say we reject the null, but in reality, the null is true. This is our alpha error. We have made an alpha error here. We've rejected a null, but maybe we just didn't have a big enough sample size. Maybe there were some other problems with the data. Either way, we made a mistake. This is where also you say someone's guilty, but it turns out they're not guilty. You can also look at it in terms of relationships, right? Let's say you're deciding on whether you want to marry somebody. What are you most worried about? Are you worried about missing out on somebody? So you just want to take a chance if they seem like a good person? Well, that's kind of what a high alpha is, meaning, hey, let's just give it a shot. There may be some problems with this person, but let's try getting married, and I may have found the good one, right? Now, of course, this box is actually where this decision to reject the null, I'm making the decision to get married, guilty, and it turns out that the null was wrong. The null that this is a bad choice for me to make, that's wrong. The person, I said the person's guilty, they were guilty. I decided I wanted to marry them, and it turns out they're a great spouse. And I rejected the null hypothesis, and it turns out the null was false. I was right to do so. Right, so this is a big smiley face box. And then the same goes for this one too. Even if you fail to reject the null, that's a good thing, of course, if in reality the null is not true. Or excuse me, the null is true. You don't want to reject it if it is actually true. So this is the case where you don't get married to someone and it turns out that, well, it would have been a bad marriage had you done it. So good job. Now the other, our beta error is right here, where you fail to reject the null, but it turns out there was an effect. So going back to the marriage example, this would be you just keep deciding not to get married to people, and it turns out you did miss out on somebody who would have been a great spouse for you. So these are just decisions and the standards for a decision that, you know, sometimes we have to make, and sometimes we maybe are guarding against the wrong type of error. And if you think about our legal system, right, especially for criminal cases, we don't want to have this situation here. We want to have a small alpha, a small chance that we say they're guilty, but it turns out they're innocent, right? We much rather have the opposite, where, you know, the better to have 20 guilty people run free than one innocent person convicted, right? We're willing to let some people who are guilty be found not guilty because we want to be absolutely sure and we don't want to make a beta or a type 2 error here. Type 2 error, which is excuse me, I said that the wrong way. We don't want to make an alpha error, which is saying they're guilty when they're not. And we're okay with a type 2 error, which is, well, you know, with the lower standard of evidence, we would find them guilty, but with a high standard, if we're not super sure, it's okay to let them go. And again, we're not happy that we made a mistake. We just want to know which kind of mistake we're most likely to make, and then choose which one we want to guard against the most. So let's get away from the examples and more into the practical, okay? And again, showing how these are related with our alphas. Again, if we have a larger part of our distribution, a bigger critical area, we're more likely to reject the null. But it also means we're more likely to make a type 1 error, reject the null, and we shouldn't. Now in this case, this is the opposite, very restrictive alpha, meaning we're very unlikely to reject the null when we shouldn't have. The problem is, though, if it's this high of a standard of evidence, we may miss a lot of real effects because we're just waiting for a stronger effect to come by. And again, going back to the relationship example, we may miss out on a lot of good potential spouses because our standards are too high, and then we never actually get married and miss out on that. Now that we're in statistics territory, we always have assumptions that go along with a test, right? Just like a criminal trial in a courtroom, we have assumptions about certain things going right and being able to trust them. But we can't just pretend that they're all right all the time. We have to actually look at them and know what to look for. And then if some of those things are a little off kilter, that will make us maybe less certain in our conclusion. So, assumptions for the Z test or hypothesis testing with Z is we assume there's random sampling. We assume there's independent observations. And this is where it's different from a courtroom. A jury, you want them to be unanimous. You want them to be influencing each other. In research, though, we want the observations to be independent. Meaning, I don't want somebody's training performance to look better than it is because someone's helping them do all the work. In that case, the observation of their performance is not independent. It's in part based on somebody else doing their work for them. Also, the value of the standard deviation should not be changed drastically by the treatment. So for example, if we previously had our untrained performance at 25 and now with a nice spread around it, high performers, low performers, and then our new training performance is everybody gets the maximum, everybody's perfect, chances are that's not a good measure of performance anymore. Chances are something weird happened with the data, and specifically that's not good for how the statistics work either. And then finally, we want to have a normal sampling distribution. It should look kind of symmetrical. Now, it doesn't have to be perfectly normal or perfectly symmetrical, but if you start having two peaks or super skewed one way or the other, you know, you want to know that. And when you present your data, acknowledge that we're making a conclusion, but our data has some problems, so keep that in mind. We can't conclude as strongly as we'd want to if we didn't have problems with some of these assumptions. Finally, it's important to look at what's known as effect size. So significance testing, we've taken a lot of effort to learn what it is and how to do it, but we can't forget about this important component too. Basically, an effect is the real thing that we care about. And this is just like our equations, the numerator is the effect, the mean difference. But we have to consider that in relation to the noise. So in some ways, I look at perhaps astronomy. You're looking at an area in the sky, and you're deciding, is there a star there? Or, we look for planets outside of our solar system. That's a long way away. Can we really tell if there's a planet there? Well, the effect is the planet's either there or not. So the effect doesn't change based on how we're looking at it. But how we're looking at it can affect whether we see it, right? And so it's important that the effect is different than just statistical significance. Statistical significance is just saying we are concluding that there's a difference, there's something there. But it doesn't tell us how big that something is. Another example could be, let's see. Oh, I had another example lined up, but I can't think of it now. Anyway, we'll come back to it as well. Oh, going back to the courtroom example. Just the jury decision, guilty or not, that's like the significance test. They made a decision. They may have made the wrong decision. We hope they didn't. But the effect size is, well, how bad was the crime? That's the more like the sentencing aspect of it. So just the guilty or not guilty is like our significance test. We want to know it, but we shouldn't stop there. We want to know more. And that's the effect size. So for example, here we see our non-trained or pre-trained score, and then group A gets a 33. That's higher than 25, but group B gets a 38, a lot higher than 25. So maybe training method B has a bigger effect, right? And so that's what the effect size is. And we'll have many examples moving forward of effect size. It's just important to think about it now for our purposes, how it's different from significance testing. So in one way, you can say effect size is about overlapping distributions. Now, one thing to see here is we see difference in the means of the distributions, but there's a lot of overlap here, right? So the effect doesn't look as strong. Now, what is one thing that will help it look stronger? Smaller standard errors make these distributions less wide, more tight, and then it'll reduce the overlap and more clearly show the effect that's there. So we have an equation for effect size, and just think about what we're doing here. Notice, mean difference in the numerator, that's the same as our z-test, or our z-statistic. It's taking the sample mean compared to the population mean. That's the effect, but now we're going back to the population standard deviation. And remember, what were we using as the denominator for our z-statistic? It was the standard error. How do we get the standard error? Well, we take population standard deviation divided by sample size. What this means is that if you have a gigantic sample size, it will be like having a super strong telescope. You're more likely to see something that's there, right? And that's good. It's more what we're going to call statistical power. But on the downside, it kind of biases our conclusion. If you just have a super strong telescope, you can see all sorts of things in the sky, but how do you tell which is more important? Maybe whether something's far away or close, two things that are different sizes can look like the same size based on how far apart they are. So what you really want to know is how big that thing you're looking at is, not just that it's there. So that's what the effect size is. And what this is doing by taking the sample size out of the denominator is to take away that kind of cheat code, or some would say a little bias, for a big sample size to be more likely to find significant differences. Notice effect size is not a significance test. It's basically just trying to take the sample size out of it and just look at the business and the mean difference of our analysis. So we can see if we have our mean differences for training program A, training program B, and then we had our population standard deviation. This is the effect size. So our mean difference for program A, mean difference for program B, divided by the population standard deviation, we see that the effect for program B is higher. Now, usually there's some sort of standard to compare effect sizes. So what we see here is generally, if we see a large, and I know, try not to giggle, but we call effect size a D. If we see a large D, usually it would be over 0.8. Any D over 1, clearly is an easy way to remember a large effect. A small effect size, or a small d, is 0.2 or less. And in the psychology types of research where we're doing surveys and other measures with lots of error involving translating internal processes from people's brains into numbers, we're just more likely to see smaller to medium effects with a lot of psychological measurement. Whereas in the physical sciences world, you're more likely to see consistently large effects. Doesn't mean small effect is not worthwhile. It just means it is a little bit less big. And that can have it has a smaller magnitude, smaller effect. So finally, we have a couple things to wrap up with that you may have been able to infer from our presentation so far, but are important to make clear. First, we can have our critical area either in the ends of each tail, the high and the low end, or we can just put that whole critical area into one tail. So if we do a one-tailed test, we call that a directional test. If we do a non-directional test, that's where we have our total alpha cut in half, and half on the high end, half on the low end. So that affects how we phrase our hypotheses. A directional test, our null hypothesis is that our mean is not lower, or our mean is lower or equal to our population mean. I think I said that incorrectly. Food consumption is not reduced, meaning our sample mean, our population mean is greater to or than equal to our sample mean. This is the key one. How do we phrase our alternative hypothesis? Food consumption is reduced. One mean is lower than the other mean. Now, for the non-directional hypothesis, we just say the two means are not different, training mean and not trained mean. The null hypothesis says they are the same. And then our alternative hypothesis says they're different. They are not equal. And we're not saying that we predict one to be higher than the other. Here with the directional hypothesis, we are predicting one to be higher than the other. And finally, we want to cover the concept of statistical power. Power kind of combines some of the decisions that we've talked about we could make before. Power is, by definition, just that the probability that our statistic will correctly reject a null that's not true, or how unlikely the test will lead to a type 2 error. Type 2 errors, we miss something because our standards are too high. The more power we have, the less likely that is to happen. We are not going to miss something. We may falsely conclude that something is there, but we're not going to miss something that is there. And we can have this formula for power. I won't put this on the exam, but essentially you'll see this a lot in statistics. But essentially our power, again, phrased differently, is the probability that we do reject a null that is truly false. We got to get rid of that thing because it's not true. So what are some of the influences on power? First, a test has more power if there's just a big effect that we're looking at. That kind of makes sense. We're more likely to look up in the sky and see a sun than we are to see a planet. The bigger the thing we're looking at, the more likely we are to see it and be sure that we are seeing it. Our alpha level, well, if we are just trying to have a low enough standard so that we're not just sounding alarms for thinking we see everything, that we're seeing ghosts, but we're okay with making a type 1 error if we want the most powerful test. What we don't want is to make a type 2 error to say, well, our standards were too high, so we can't make a conclusion. So that means we're going to have, instead of an alpha of 0.0001, the higher power is an alpha of 0.05 from the values we've looked at. Also, a one-tailed test will also have higher power because we put all of that critical region into one tail instead of splitting it up into the two tails. And then here's the major cheat code for power as well. Bigger sample size will lead to more statistical power. And so power, again, is talking about the significance testing. So more likely to conclude significant difference, reject the null. Sample size, the bigger we have, the more likely we can do that. But that's why we also have effect sizes, because you don't want to have your entire decisions based on sometimes rigged for high sample size conclusions. You don't want to just say everything that's significant is important, because some things with a big sample size are significant, they are there, but they aren't important. They don't have a big effect. And so just because they're significant, we don't want to conclude that that's the only thing that drives our determination of them being important. So lots of stuff that we covered. Hope you're able to hang in there, because we will be coming back to all these issues, especially alpha, type 1 errors, 1 and 2-tailed tests, power, and especially effect size. All those things, I know they might be new for the moment, but we'll continue to be talking about them throughout the semester and anytime beyond this class when you encounter statistics.